Okay, good afternoon, ladies and gentlemen. Thank you for attending our seminar today. Today's speaker is Professor Yvonne Stokes from the University of Adelaide, where she did her PhD in applied mathematics. In addition, she did her postdoc at the University of Adelaide, where she was an ARC postdoctoral fellow for 3 years, and she's now a professor there. She's published in a panoply of different journals. So in addition to the usual suspects in fluid mechanics, she's also published in several biological journals. So she has a diverse range of interests that mostly center around viscous flows and particle-free surface flows. In addition to her position at University of Adelaide, she's also a member of the Australian Academy of Science National Committee for Mechanical and Engineering Sciences. And she is also on the executive committee of the Women in Mathematics Special Interest Group of the Australian Mathematical Society. And for those of you who attended the 2018 Australasian Fluid Mechanics Conference, she was one of the keynote speakers there. And she gave a very nice talk. I think it was on the 4th day of the conference, if I remember correctly, where she compared theory, CFT, and experiments. And correct me if I'm wrong, but I remember that theory agreed with the experiments better than the CFT, if I'm not mistaken, which was, as someone who works in theoretical stuff myself, I was very happy to see that. So without further ado, I'm going to allow Professor Stokes to start our talk. Thank you very much for agreeing to talk with us.
Thanks, Sean. So I'll just share my screen. I've lost my talk, so I'm going to find it. Okay, so okay, so hopefully everyone can see my screen now. So I'd just like to start by thanking the organisers for giving me an invitation to speak. It's a bit of a different forum, and I think it's a great idea actually in the current circumstances. So thanks for organising this whole series. So today I want to talk to you about some work that I've been doing over about a bit over 4 years. So on inertial particle focusing in curved microfluidic ducts. As Sean said in my introduction, I'm an applied mathematician, so it's reasonably theoretical, but hopefully I've got it at a level which everyone can understand. So just to start out with some acknowledgement, so this work wouldn't have happened actually without the support of the Australian Research Council, so and also my own university have put money into my research, which has been much appreciated. And the work has also involved a really very quite smart postdoc, so Dr. Brendan Harding here, who's been working with me over about 3 years. He's just finished and heading off to New Zealand. And it's also involved Professor Andrea Bertozzi at UCLA. So my work was motivated by something which is depicted here in the picture on the left of this first slide. So this is a microfluidic sorter, and it's just a spiral microfluidic duct as shown here. And these are used for sorting particles by size, so normally close to neutrally buoyant particles, and in particular cells. So I saw an article on this in the Physics Today back in 2014, and that's what really sparked my interest. So these are used, you take a blood sample, it's normally a bit modified, so they remove red blood cells, but the idea is to screen this blood sample for circulating tumour cells. So tumour cells are much larger than white blood cells. So you take a mixture here, which is shown in this little test tube on the right, and it's pumped along this spiral microfluidic duct. And what happens because of the flow in this duct, the cells separate by size. So the idea is that they separate by size, and at the end of the spiral here in the centre, the flow stream is split into two, and one of which is collecting the circulating tumour cells, the large cells, and the other one is collecting the rest of the blood cells. So that's the idea, and the reason that you get this separation is because you get a secondary flow, or a flow in the cross-section of the channel, so that's depicted here at the bottom, and you get small cells going to the outside of the channel, on the outside of the bend, and larger cells going to the inside of the bend. And hence you can split the flow sort of through the middle to separate these two. So that's the idea. Okay. So particle focusing due to inertial lift was actually first reported in a Nature paper in 1961, authored by Segre and Silberberg, in which they reported the migration of neutrally buoyant spheres in flow through a straight cylindrical pipe. So that's depicted here on the left-hand side. This is the pipe, so the flow is coming from the top and going towards the bottom in this picture. And initially the flow is a mixture of water and spherical particles, which are buoyant or neutrally buoyant. And as they flow through the pipe, they observed that these particles migrated towards an annular region. So as you're coming down the pipe, the particles are becoming more and more concentrated in this sort of little band on the side. So they've actually migrated across the pipe to this annular region, which is about 0.6 of the radius of the pipe. So that was their work in 1961, and this sparked a lot of experimental and theoretical study from that. So just a few pieces of information on that. So it was shown by Mattis and co-workers in 2004 and 2009 papers that the radius of this annular region in which the particles collect increases with the Reynolds number. With respect to more experimental investigations, we've seen inertial lift being investigated for separation of cells by size by DiCarlo and his group. They reported it in a paper in 2009. So DiCarlo is based actually at UCLA, where Andrea Petozzi is, and is helping us with some experimental work. And also by Walkiani reports this too in a paper in 2014. Walkiani is based in Sydney, Australia. So there's been a lot of work, but much of the behaviour is still only understood at an empirical level, especially once you get to complex geometries. So there's lots to be done. So just starting with some straight rectangular ducts. So studies were done by DiCarlo and others, and they showed that neutrally buoyant particles migrate towards one of four equilibrium positions, which were located at a finite distance from the centre of each wall. So I've depicted this at the bottom. The picture here is was actually computed by my postdoc, Brendan Harding. So it comes out of our work. We've got a square cross-section duct on the left and a rectangular one on the right. And this, I've just put them here to illustrate what all the words mean. So what it's showing, the green points here are stable equilibria to which the particles migrate. The black lines are showing trajectories of the particles depending on where they start in the channel cross-section. And the yellow dots are like, they look like, I've just forgotten the word, where you have a, in a dynamical system, a particle goes towards and then away from it. This in the centre is a red dot, is like a source. The particles will always move away from that point. So anyway, what you get is these four positions at the centre of the walls and just off the edge where the particles migrate. And that's been shown by DiCarlo and others in experiments. You get it also in a rectangular duct. So again, it's the same behaviour, but it's just a bit stretched out. So this work, this type of flow in straight ducts was studied by Hoodley and Roper. Caitlin Hood did it for her PhD. And some work is published in JFM in 2015. And they developed a model of an inertial lift force at a small particle Reynolds number for these neutrally buoyant particles in these types of channels, and showed that it agreed reasonably well with experimental data. Caitlin, in her PhD thesis, showed that when you get it into a rectangular duct instead of a square duct, the size of the attraction zone for the equilibrium near the side walls decreases. And you can see that in the picture at the bottom here. The 2 points on either side have a very small region of the flow from which they'll attract particles. And most of the particles in this cross-section would go to one of the top or bottom equilibria. And if the particles get big enough, you can actually lose these two equilibria on the side walls. So I'll show that a bit later. Other studies have indicated that you get less focusing at high flow rates, and that suggests that low flow rates are more suitable for cell separation and sorting. So now to come to curved ducts. Work on curved ducts has been largely focused on experimental studies by DiCarlo, Walkiani and others. And it's shown that when you have a curved duct, the ducts are quite effective in separating particles and cells by size. You'll see why in a little while. A small height relative to the width of the channel is favourable to focusing particles by size. We've sort of seen some evidence of that in the previous pictures I just showed for a rectangular duct, but symmetry means you get multiple focusing points, whereas once you put curvature into the channel, you actually break the symmetry, so you can start to get more focusing to one point. So the reason for the focusing is this secondary flow that develops because of the curvature of the duct. So I've got two pictures here. The one on the left is axial flow contours. So you get quite a strong flow along the axis of the duct, sort of down the duct, and these are contours from maximum flow here at this point. I want to say in the centre, but it's right on the edge. But anyway, where this closed inner ring is, and then you go to no flow, of course, with no slip boundary conditions on the edges. This is a trapezoidal shaped cross section. So that's the axial flow contours, and then on the right we have streamlines of the secondary flow. So what you get is two counter-rotating vortices here, with the flow sort of flowing outwards. So the inside of the bend is on the left. The flow goes out more or less along the centre of the channel and then either up or down, and you get these top and bottom counter-rotating vortices in the cross-section. So this is, it's been known for a while, so it's called Dean flow, attributed to Dean, who first wrote about it in 1927. He looked at it in the context of a circular pipe rather than a trapezoidal cross-section, but it's the same thing. So size-based separation of neutrally buoyant particles is due to an interplay between inertial lift, which even happens in straight channels, but in addition you get this drag forces coming from the secondary fluid flow, and actually a bit of inertial resistance to changing direction of the particles plays a role too. So the inertial lift, just to, I haven't commented on this, but let me just point out, inertial lift is primarily due to the axial flow and is caused basically by the fact that you have a finite sized particle. Different sides of the particle see different fluid velocities and therefore different pressures, and you get a net force on the particle, which causes it to drift off a streamline of a flow. So coming back to liquid biopsy, which I mentioned right at the beginning, liquid biopsy is the name given to isolating circulating tumour cells from a routine blood sample. This little quote from the paper in Molecular Oncology just says that it's important because circulating tumour cells hold great potential to transform the current landscape of cancer therapy. So if you can isolate circulating tumour cells, then you can, and characterise them, you can get some idea of what's going on with a cancer. So hence isolating these cells is important. And they're actually quite rare in the blood. I mean, we have a lot of cells in our blood stream, and finding circulating tumour cells among them is quite a challenging task. So if you can get hold of these circulating tumour cells, you have some idea about a patient prognosis. So obviously if there are none, you're not expecting metastasis of a cancer. But if you're starting to identify circulating tumour cells in the blood, then you can expect the cancer to spread to other places. So it tells you something about the progression of the cancer and the prognosis for the patient. You can also perhaps get some idea of response to drugs and other therapeutic action, maybe radiotherapy or something, and perhaps look at new therapeutic targets, look at drug resistance, all sorts of things that you could look at if you can isolate these cells. So 90% of cancer-related deaths are due to metastatic cancer arising from circulating tumour cells, and so improving liquid biopsy has the potential to actually improve the lifespan and treatment of cancer sufferers. So it's a pretty important thing. So this brings me back to the spiral inertial microfluidic sorter. It's not the only method available for isolating these circulating tumour cells, but it is one of the most promising methods. So actually the paper in Physics Today went through a variety of methods, but some of them sort of filtering start to damage cells, so that this one is good because it doesn't do that. So a commercial version has actually already been developed by Biolytics Proprietary Limited. They're a Singapore company. It's called the ClearCell FX1 system, and a paper was published in 2018 on this. It's a simple device. It's robust. You can get a high throughput, and you need to get a high throughput if you're going to isolate a few cells from a blood sample. You need to get a lot of blood going through it. And it also has minimal impact on the cells. The difficulties with it are actually isolating the cells. So you don't necessarily get the separation of the large and small cells as cleanly as you want, and so you get leukocyte contamination, and that's not desirable. So that's one of the problems. And so to fix this, you need some quantitative understanding of how the geometry, the particle size, the flow rates affect the separation of particles. And then you can also get some idea of operating parameters for these devices. So that's what's motivated the work I'm going to talk about here. And we've developed a model to give insight into how this interplay between inertial lift, drag forces, and drag forces lead to focusing positions that differ with particle size. It's extending the work of Hoodley and Roper in JFM 2015, which was for straight channels, and we've really just added the curvature, but that has changed things quite a lot. So some model assumptions. I'm going to be fixed here on rectangular or trapezoidal cross-sectional geometries. although it's not essential to the model. We assume a long duct, so lots of turns of the spiral essentially, and neglect end effects. We also take a dilute limit and only consider a single spherical particle. That's you know, quite questionable. It's not totally, a lot of experiments are done with fairly dilute particle concentrations. So in that sense, it's good. It doesn't seem right for blood, but finally, when they take a blood sample, they do dilute it, remove red blood cells and modify it substantially. So we hope this is not too bad an approximation, but anyway, it's a good start. We're going to neglect gravity and assume the particles are neutrally buoyant. I'm also going to take a constant bend radius. This is not too serious a change, because if you have a bend radius that's changing relatively slowly with distance down the channel, you can just look, you can look at the constant bend radius and apply it locally at different points in the down the channel, and just look at a different local bend radius and get a very good idea for what's going on. So we've got a pressure-driven viscous flow. This is quite a relatively slow flow compared to some. We've got an axial flow velocity along the duct, which is large compared to the secondary flow velocity. So that's going to play a role in the model. Far from the particle, the flow is that of a particle-free fluid. So that's what we're going to call the base flow. And I'm going to be assuming here that we know the base flow. Near the particle, the base flow is perturbed by the presence of the particle. Next assumption here that we've got slow migration of the particle in the cross-section compared to its axial velocity. So the flow in the axial direction is quite strong relative to the flow in the cross-section. So the particle is going to move more quickly in the axial direction compared to the cross-section. So it's going to migrate much slower than it's moving downstream. So we're going to make this sort of approximation that the particle roughly follows a streamline of the base axial flow component. So that'll be one of the assumptions that is made in the model. And then we're going to think about the particle motion being perturbed in the plane of the cross-section by drag force from the secondary flow, inertia due to the curvature of the path, and the inertial lift force, which is primarily due to the axial flow. Okay, bit of nomenclature and coordinates now. So this is a lab reference frame. As I said, we're going to assume that the bend radius is constant. So we've just got a piece of duct here, which is shown as a rectangular cross-section. The radius from the origin here of the XYZ coordinates to the centre of the duct is capital R. This picture over here shows the cross-section. It has a height, capital H, and a width, capital W. We're always going to take the width as being larger than the height. It can be equal if we have a square duct, or it's going to be larger. We set up a sort of local coordinates here, little r and little z. So with the origin at the centre of the duct cross-section. So the distance from the XYZ origin to the to some point in this channel is big R plus little r, the little r coordinate. So we're actually going to work in this little r, little z coordinate scheme. Okay, so the position, any position in the duct is given in terms of an angular coordinate, which is sort of an angular distance downstream, if you like, from the x-axis. So that's a theta, and then we've got this r and z coordinates. So this, we can write a Cartesian coordinate position in this in terms of the cylindrical polar coordinates, r, theta, and z. We denote the position of the particle by putting a subscript P on it, and that changes over time. And little a is the particle radius. Oops, wrong way. Okay. So for the model in the lab reference frame, we need to determine the base Dean flow. And to do that, you have to solve a steady pressure-driven incompressible Navier-Stokes equation subject to no-slip boundary conditions on the duct walls. And I'm going to take this as known, that this base flow is known. So the base flow has these sort of bars for the velocity and the pressure over it. So it's assuming that the particle travels or nearly travels along a streamline of the base axial flow component. I'm going to say that it has a constant spin. That's given by omega p. So the angular velocity here is the rate of change of its angular coordinates, so that's theta p with respect to time, and we're going to assume that's constant. And for a constant base flow, that seems reasonable. And because we're assuming it stays on this a streamline of the base axial flow component, we have that dr and dz dt, the time derivatives of the radial and vertical coordinates of the particle, are zero. So this is an approximation, but it's true. We sort of make this assumption and then work out what the forces are on the particle and how it would move off this position. And we're also going to say that its spin doesn't change with time either. So what that means is that the position of our particle, x subscript p, is given by a theta, which is just my angular velocity times time, and its r and z coordinates. And I'm taking that at time t equals 0, its theta coordinate is 0. So you then have to write down the unsteady pressure-driven incompressible Navier-Stokes problem for this flow U and pressure P, which I haven't got bars on because now we're talking about the flow with the particle present. It's subject to no-slip boundary conditions on the duct walls and on the particle surface. And then in the far field, you should get the base flow back. You can also write down expressions for the force and the torque exerted on the particle by the surrounding fluid, and which will drive the particle motion. So that's the sort of, in words, what the model looks like. We then move to a rotating reference frame. In the lab reference frame, this is an unsteady problem because the particle is moving along downstream. But we define a rotating reference frame about the z-axis with a constant rotation rate of big theta, which is the rate at which the particle is moving in the theta direction. So actually we're moving along with the centre of the particle along this duct. So primes on variables indicate that we're now in the rotating reference frame, so we can write our coordinates in this rotating reference frame. And in this rotating reference frame, the particle centre is always at theta equals 0 and at its R and Z location. So now we're sort of riding along with the particle down this duct, and in that reference frame, the flow looks nearly steady. So we can sort of throw away time derivatives. So we have to move our velocity and pressure into this moving reference frame. The velocity, we just have to sort of actually, this U is the flow in the fixed lab reference frame, and I'd have to subtract the flow component, which is due to our moving along with the particle to get to the primed flow, which is the flow in the rotating reference frame. The pressure actually doesn't change. So you rewrite the flow problem in your rotating reference frame. You need to write the base flow in this reference frame. So this is the primed one is with the bar over it is the base flow in the rotating reference frame. And again, you need to write down expressions for the force and the torque on the particle in the rotating reference frame, and this is just a matter of integrating the stresses over the surface. Okay, so I haven't written them here. They get reasonably complicated to write down, but it's just an integral of stresses on particles. Okay, so after we've done that, we then work out what the disturbance flow is in this rotating reference frame. So we've got our base flow in the rotating reference frame, which has got this bar over it with the prime, and we've got our flow in the rotating reference frame with the particle present, and we look at the difference between those two, and that is what we call the disturbance velocity. So that's V prime. And similarly, we can get a pressure disturbance as well, which is Q prime. So you can rewrite the whole problem in terms of these disturbance velocities and pressures, which is what we do. And we just end up solving for the disturbance from the base flow. You can scale your problem. So I've written some of the scales down here. So you just got to choose your appropriate scale. So in the way the model's done, we're scaling lengths with the radius A of the particle and so on. And when you do that, you get the dimensionless problem that I've shown here. So this is my momentum equation first up. And this Reynolds number here is what we call the particle Reynolds number. And it's defined at the bottom. So the flow Reynolds number here is rho h on mu. H is the height of the duct. Is the velocity of the base flow at r equals 0 and z equals 0, the origin of our coordinate system, or at the centre of the duct, if you like. And then the particle Reynolds number, you're multiplying by the square of the ratio of A and H. So A is much smaller than H. It's the radius of the particle and then divided by the height of the channel. So it's a much smaller quantity than the flow Reynolds number. So that's what we get here. A fairly standard continuity condition. We've got the disturbance flow in the duct wall has to be 0. And then this is how the disturbance looks like on the particle surface. But essentially we've just got no slip on those things. But because we're in a moving reference frame, it looks like this. So typically the Reynolds number for the flow is between 1 and 100. And so our particle Reynolds number is about 2 orders of magnitude smaller than the flow Reynolds number. And again, you have to get expressions for the force and torque by integrating stresses. Okay. So having got that problem, we assume that the particle Reynolds number is a small quantity, so much less than 1, and do a perturbation expansion in powers of this particle Reynolds number. So here we have our disturbance velocity written out as a leading order term, first order term, and higher order terms. Same with the pressure. So you substitute those into the equations and then take the leading order terms and you get the leading order problem. And it looks much, much simpler. So now we've got essentially Stokes flow problem here, continuity, and then our boundary conditions on the duct walls and on the particle surface. We can also get the next order problem, the first order problem, which looks like this. So that's where we stop. We don't go to higher order than that. So it comes down to solving these problems in order to get the solution. You have to, well, here's our force. We write out the force and torque also in powers of the particle Reynolds number, and we get the first term in terms of the inverse of the particle Reynolds number. So this can be quite a big term. These forces and torques can be quite efficiently computed using what's called the Lorentz reciprocal theorem. We followed the Hood, Lee and Roper paper to do this, and I'm not showing the details here. This is my angular velocity in scaled coordinates, the particle spin, and these are chosen such that the components of this leading order force and torque due to the axial velocity component are 0. So essentially you're sort of saying that this particle is going down the channel in the axial direction without experiencing any force in that direction. It's just moving along, certainly in the reference frame we're working in.
Hey, Yvonne.
Yeah.
So Methma had a question in the chat box. Are you happy to address that?
Yeah, I can't see a chat box, but
that's okay. So the question was basically, why is the particle Reynolds number scale multiplied by the Reynolds number by A on H squared rather than just A on H?
It's just the way it yeah, you'd have to look at the maths to see that. It's the way it comes out in the scalings of the problem. So
it's when you non-dimensionalize things and the length scales that come out during that process, is it?
Yeah, that's right. You just have to look what the maths tells you. And the maths has gone into in detail in a paper that came out in JFM last year. So yeah, if you're interested, have a look.
Cool, thank you.
Yeah. Okay. Okay, so where was I? Okay, so we're going to take the force and torque given by these two equations here. So we're neglecting terms that are order of the particle Reynolds number and higher, and just taking the first two terms. And so given a fixed particle size and a duct size and shape, then you can work out this force on the particle as a function of its position within the cross-section. So that's what we do. So we take a position, we compute the flow, we integrate the stresses over the surface of that particle to get the net force on that particle. And then from that, you can compute the trajectory of the particle within the cross-section based on its terminal velocity. So that's the velocity in this RZ direction in the cross-section of the duct, such that the drag force is equal and opposite to the perturbing force. So when you do that, now we're going to have some pictures. Sorry for all the maths, but now we'll have pictures. You can plot a force field. So what I've shown here is the force field in both straight and curved square ducts. So the width to height ratio is 1. I'll just comment here that I'm now scaling lengths with h on 2 instead of the radius of the particle. If I did it with the radius of the particle, my particle radius would always be 1. But it's sort of convenient to keep the size of the duct fixed and have a small particle in the way you look at it. So that's what's been done here. So the top set of plots here, the 4 at the top, are for a curved channel, so with a bend radius of 160. And relative to a duct height of 2, because I'm using h on 2 as my scale. So this is a fairly large bend radius, and we've got 4 different particle sizes, 0.05, 0.1, 0.15 and 0.2. The bottom set of cross sections are for an infinite bend radius. So this is the straight channel. So I've just put these two together so you can see the change that's being brought about by a curvature in the duct, the bend radius. So the ones at the bottom there, you notice they're all symmetrical because there's no bend in the channel. So we have both top, up, down and left, right symmetry because it's just a straight square channel. With the top set, we have broken the left, right symmetry. We've still got top, bottom symmetry, but we've broken left, right symmetry because of the bend. The bend, the inside of the bend is on the left side, always, of the duct. So the colour here, if you have a dark blue, you've got 0 force, and up to the lighter colour is the sort of higher values of force. There's some white and black lines that you'll notice. So maybe if I just take this first picture because it's most obvious, the white curves here are the contour of 0 vertical force. So if you're sitting on this white line anywhere, the particle would be feeling no force in the vertical direction. And if you're on a black contour, the particle would be experiencing no force in the horizontal direction. So if you're at an intersection of a black and white point, the particle is experiencing no force in the cross section, right? So it's an equilibrium position. Now the arrows here, you see these black arrows. It says that because I've come below this black contour, the force is to the right. But if I go above the black contour, the force will be to the left. And if I come down below this black contour at the bottom, the force is also to the left. So we're getting a switch in direction as you cross this black contour from to the left to 0, to the right to 0, to the left. And similarly for the white, now this is vertical force, we've got the force being down or towards the centre, up from the lower half of the channel and down from the top half of the channel, out here. And then as we cross this vertical piece of the contour, the force direction switches. So you can sort of infer what goes on. We don't have in this cross-section any stable equilibrium. There's an equilibrium here, but you can see if I move left or right, I will move away from it. Okay, so this is not stable at all. And the particle will, in this case, a particle will actually cycle around, will actually go into an orbit. Okay, but if we come down to the straight channel case, I don't know, you can just see that there's an intersection, say, of a white and a black here, and this is actually, based on the direction of the arrows, a stable equilibrium. But over here, we have a saddle. Okay, we have the flow, the particle will do this sort of thing. If I hope my red dot's showing up, you come down from the corner and then come down and away from this point. It acts like a saddle. So we can use these force diagrams to work out what's going on, what the particles will be doing and how they'll move. So this is just some pictures now showing approximate trajectories of particles from different positions in the channel, corresponding to those force plots that I showed earlier. So once again, we've got the top row, which are for a channel with a bend radius of 160 and 4 different particle sizes from small to large. That's from left to right, small on the left and large on the right. And below, we've got the straight channel to compare with. So for the straight channel, you can see we always have these 4 green dots, which are the stable equilibria for the particles where there's no force, and they'll just sit there. We've got saddles at these 4 corners, and we've got like a source, if you like, at the centre. The particle will always move away from here. And that never changes with the particle size. As we move across this set of cross sections and the particle size is increasing, that's all that's happening. Just to comment that this red dashed line would be the centre of a particle when its surface was touching the edge of the duct, so you can't sort of go past that red dotted line. So nothing changes much really with a straight channel, but when we have a curvature, we get quite a significant change. So this left thing, the particle follows some sort of spiral path inwards towards this red dot, and then it hits this green curve, which is an orbit. It's a stable orbit, and it will just follow this orbit round and round and round. If you started inside near the red dot, you would spiral out onto this orbit.
Yvonne?
Yeah?
We just had a question from Ray, who's asking why there isn't an equilibrium on the edge of the square.
On the edge of the square?
Mm.
You mean in the bottom straight ones or the top ones?
Ray, do you want to qualify that? Unmute and qualify? He says the top ones.
So the top one, well, it's to do with the force fields I showed earlier. We have an equilibrium here, which is a saddle. So it's not stable. The particles won't go there. So depending on the size of the particle, etc., it could be sort of meant to be out here. Mathematically, it's just not within the flow domain. Particle won't go here. Is this where you're expecting it? It sort of looks like there could be one, but I think mathematically it's not there. So you'll always get some motion inwards. Okay, so here we have an orbit. When we increase the particle size, we have a lot less circling around to get to the orbit, but we still have a stable periodic orbit here. And then increase the particle size again, and suddenly the orbits vanish and we get a stable equilibrium. And now all of the particles are moving to this stable equilibrium, okay, on a fairly direct trajectory, and sort of come up onto this slow manifold and then come along down to the stable equilibrium. Okay, and increasing the particle size further doesn't change that. So you're getting a very different behaviour as you're going from a particle size of 0.1 up to a particle size of 0.15 here. Okay. So now this next set of plots is just showing you the effect of the bend radius. So I've got the first two on the left are showing for a particle size of 0.1 and a bend radius of 210. So again, we're getting a stable orbit, and then changing the bend radius to 220 from 210, we suddenly get a stable equilibrium point. So now the particles will focus and not travel around on an orbit. On the right, we've got a similar thing for a bit of a larger particle, so 0.15, radius of 80, and that's the bend radius, and you'll get these tiny little orbits here that'll go around, increase the radius to 90, and now we get a focusing point. Okay, so that's just some idea of how the bend radius and the particle size affect what happens to the particles, whether they focus or whether they don't. Okay. So now we're changing the duct shape from a square to a rectangle with a width to height ratio of 2. But we get somewhat similar behaviour, a very small particle size, bend radius of 160, that's the same for all four at the top, and we get, it looks like it's an orbit, but actually it does go in this case to a stable focusing point, one in the top and one in the bottom. It just takes a fair while to get there because it rotates round and round for a while, but it does reach a stable point. Increase the particle size and you get there much faster. And the position has changed a little bit too. It's gone to the left. Increase the particle size again and it's gone slightly to the left. It's not moving very far. Increase the particle size and it's actually come back to the right. So depending on the particle size, you're getting different focusing points here. At the bottom here, we've got the straight channel case again. So again, we have 4 stable equilibria for the small particle size. Increase the particle size, and now we've lost the stable equilibrium on the left and right hand walls, and we've just got a saddle point there. So that's just because the particle size is increased. But the stable equilibria on the top and bottom are always in the centre of the channel because we don't have any break in the symmetry. This is a symmetrical problem. Okay, what am I doing for time? Now I've increased the width of the duct so that it's 4 times the height, and this the behaviour is quite similar to what I showed before. Now I've got 4 plots on the right for a bend radius of 160, and the 4 on the left, and 4 on the right are for a straight channel. But what we see here, just because the channel is longer, is a much bigger shift in the position of the stable equilibria. So you can see you've got these 2 here, for the small particle size. We've increased the particle size from 0.05 to 0.1, and the stable equilibria has moved to the left. And it's moved more than we get with a shorter, with a smaller width channel. Okay, this one didn't hardly moved at all, and then going up to 0.2, it's come back to the right. And this is the straight channel case again, which is quite similar to the previous set of plots. Okay, so we decided to plot the focusing location as a function of curvature, or actually an inverse curvature here. So this is twice the bend radius divided by the height of the channel. And this will be large. Normally the height of the channel is quite small relative to the radius of the bend, and sort of geometrically needs to be to make one of these spirals. And you can plot the focus. So this is, on the left we've got W on H is 2. So the width is twice the height. And we're plotting this inverse curvature. So the radius is getting larger as we go to the right. L is the same as big H here. And you're plotting the focusing location here in the lower half of the channel, because remember there's top-down symmetry. So you could sort of flip this up around this y=0 thing and get a similar picture in the top. Just be a mirror image. Okay, so these are the focusing locations. The blue is for the smallest particle size, 0.05, the green for the next one, 0.1, the red for the 0.15, and the light blue for the 0.2. And then on the right here, we have the same set of curves, but we've increased the aspect ratio of the duct. So there's not, you know, you just get a different curve for a different particle size. Now, what's interesting is the next one. So we define this parameter. Actually, Brandon found this parameter. Again, it comes out of the looking at the scaling in the mathematics, kappa. And it's really just the ratio of the secondary flow drag to the inertial lift force. And if you choose to plot the focusing location as a function of this parameter kappa, then we get this remarkable collapse of curves onto one another. So remember, sometimes there are multiple stable equilibria in the cross section, and sometimes there are not. So these extra pieces are where there are two, but we've got collapse of a whole lot of them onto this curve. So you get really good collapse when kappa is relatively small, okay, less than 10. Once it gets larger, so that tells us that the secondary flow is starting to dominate the inertial lift, we have less of collapse. But if the inertial lift is dominating secondary flow, we get this really good collapse of the focusing location onto one curve, no matter what the particle size. The particle size is involved here in the definition of kappa. So what this tells us is that we can use this kappa parameter to sort of predict focusing location for different bend radii, particle radius and height of the channel. The aspect ratio changes the plot a bit, but you still get this nice collapse. So that's one thing that came out of our work, which we thought was pretty good. So we've also looked at trapezoidal ducts. So once you change the shape, so here we've just put a slope on the top surface of the duct, we now break the up-down symmetry as well as the left-right symmetry, which is broken by the bend. So again, on the left, I've got plots of the trapezoid for a bend radius of 160 for 3 different particle sizes. And on the right is the straight channel case, R going to infinity. So for the straight channel, I've got actually a stable equilibrium right here next to the wall, 2 saddles. A red dot means it's like a source, And then I've got these two stable equilibria here and here. I've got a saddle down here as well. It's a bit hard to see the size of the dot is small because it's a small particle. Okay, so things don't change much with particle size, okay? It's changed from a rectangular channel to a trapezoid, so that's changed the behaviour of the particles for the straight channel case, but it doesn't change much from one particle size to the next. However, once you have a bend, okay, we've got two stable equilibria here, and then suddenly increase the particle size from 0.05 to 0.1, and our stable equilibria have moved right to the other side of the channel. This is a massive change. It just shows you how particle size can affect where things go, and the extent of the change is also being influenced by the fact that we've now got this slope on the top wall of this duct. Change the particle size again and it's come back. So you can start to see how you can potentially tune things for different particle sizes and perhaps get some separation. So once again, you can plot the focusing positions. We no longer have up-down symmetry, so this is not just focusing, not just plotting for half of the channel, it's plotting across the whole of the channel. We've always got these sort of two curves. So on the left, we're plotting focusing locations versus the inverse curvature, and again on the right versus this kappa, the ratio of the drag to the inertial forces. And again, when inertial force dominates, we get a very nice collapse of these curves. Okay. This is just to show how things can change a lot. So just here change the bend radius of the trapezoid from 160 down to 80, and suddenly we get 4 stable equilibria and a couple of extra saddle points. So bend radius matters as to what happens to the particles. We've gone on and added the effect of gravity. I don't know, I'm just about out of time, I think. Is that right?
Yeah, that would be great, Yvonne, if we could field some questions soon.
Okay, so I'll just say that we've looked at gravity and the effect of gravity, and let me just flick over this quite quickly and just show you some pictures when gravity is quite significant. So this is with a Froude number of 1, and now you can see depending on what happens. So this set of plots in here, okay, there's different particle sizes from top to bottom and different density differences between the particle and the fluid from left to right. So a density difference of 0 means a particle has exactly the same density as the fluid. So this is sort of cases we've already seen. If I make the particle buoyant, we get the pictures on the right, sorry, on the left here. If I make the particle denser than the fluid, we get the pictures on the left. So gravity makes a big difference as well to what goes on. So I won't dwell on that any further because we're out of time. Just pop up my conclusions. We've developed a general model for the forces that govern the motion of a spherical particle in flow through a curved duct with constant bend radius. We've only looked at rectangular and trapezoidal cross sections, but the model is not at all restricted to those geometries. We could look at others. We've seen that the cross-section shape, the bend radius, the particle size and gravity all affect the focusing position of particles. We've got this parameter kappa, which seems a good predictor of focusing location for neutrally buoyant particles, at least when the inertial lift force dominates the secondary flow drag. Gravity modifies that a bit, but I haven't really got time to talk about it. And we've got lots of future work planned. Experimental validation was sort of going to happen. COVID sort of shut labs, so this has been a bit delayed, but hopefully we'll get some experimental validation going with the DiCarlo group at UCLA. One thing we've started work on, but I haven't talked about, is how things evolve over time. I've just looked at sort of long-term steady state positions of particles, but the time they take to get there obviously affects you know, the length of a duct, of a spiral duct that you would need in order to get focusing. And we could explore other cross-sectional geometries, and there's a bunch of other things. So I'll just stop there. There's a couple of papers if anyone's interested. This one in JFM 2019 goes through the neutrally buoyant work, and we've just had one accepted by JFM, so it's about to appear on the work with gravity. So thank you.
Thank you, Yvonne. Did anyone... Oh, sorry, Sean, I wasn't sure if you were there.
No worries. Go ahead.
Does anyone have any questions for Yvonne? I've got a question while everyone's just collecting their thoughts. Where you have that transition between those two upper and lower stable states, and then the as you increase the particle radius or the radius of the channel, you get back to the situation in the straight channel. That transition, is that where the leading order force balance changes? Is that what drives that transition?
Let me just see if I can. So you're talking in the neutrally buoyant case?
Yeah, quite a few slides back. I'm wondering if it's related to kappa or something else. So yeah, a bit further back still, sorry. Maybe one more.
This one?
Yeah. So where you have that transition, is that due to a change in the leading order force balance, or why is that transition there?
You mean from the rotating, the sort of being on an orbit to going to a fixed point?
Yeah, exactly.
Yeah, so what's happening here is that the particle is really small, and so it doesn't feel much inertial lift. Because there's not much change in pressure from one side to the other, and it's being carried, it's experienced a lot of drag from the secondary flow. So it's essentially being carried by the secondary flow. There's a bit of inertial lift, but it's really settling down and rotating with the secondary flow, which is sort of in the background here. It's not pictured. So when you have a small particle, it gets carried with the flow and not much affected so much by inertial lift. And as soon as you increase certainly if you increase the particle radius, that can change. And so by increasing the radius, okay, you're reducing the secondary flow.
Right, okay.
Does that make sense? Because there's less curvature, so it's not so strong.
So, or otherwise it's the pressure difference across the side of the particle, basically.
Yeah, so as you decrease that, it sees less inertial lift.
Yeah, okay. Ray's got a question. Thank you for that. Ray, did you want to unmute and ask your question?
Yeah, actually you mentioned earlier that this model can be used for tumor cell separation, but is there any other application such as oil refining?
There are other applications of this thing. You can, so someone in IPAS actually showed me for putting minerals down here, like finely ground minerals. I haven't really looked a lot at other applications, but mostly these microfluidic ducts seem to be looked at in the context of cells and cell separation, but there's no reason that it couldn't be applied somewhere else, to my knowledge. Providing people are interested in separating things at that sort of micro scale, it would be an appropriate model.
Okay, thank you.
Did we have any other questions? Takeshi, were you happy with the answer you got from Brendan?
Oh yes, I'm happy with the answer from the Harding already.
Okay, yeah, great, awesome. So we've got a question from Dalton. Did you want to unmute your microphone, Dalton, and ask your question?
Yeah, sure. Thanks. That was a fascinating talk. These streamlines are so pretty. I was just asking, maybe I missed it, but how do you solve the perturbation equations? And you could solve this directly. You could solve the Navier-Stokes directly in a moving reference frame. What's the advantage of solving the perturbation equations?
I guess it's just a simpler, it's pretty complicated actually if you look at well, I haven't even written all the equations up. These are much simpler problems. So I guess we may have to start solving things more directly. I don't know if we want a higher Reynolds number, but certainly for low enough Reynolds number, you can pick up the basic behaviour and do more analysis more easily with a simpler problem. So we are solving these numerically, however. And yeah, I guess it's...
No, I understand. That's
yeah, how many terms you want to include in all your equations.
Yeah, thanks a lot.
Yep, Avind, I'm sorry, I can't pronounce your name. Aravind, did you have a question?
Hi, thank you. Are you able to hear me? Can you hear me?
Yep.
Yeah, thank you. Thank you so much for your talk. Actually, I'm a PhD student from University of Melbourne. I'm working in microfluidics. So I recently experienced a particle migration for my experiments. And there are two questions I would like to ask. One, you mentioned about the particle size. Is it non-dimensional number you have put an input, or is it like the micrometer scale, like 0.05?
That's a dimensionless number, yeah.
Sorry?
It's a dimensionless number. It's been scaled with the half height of the channel.
Okay. Second thing I would like to ask, like, does it have a very strong dependence of Reynolds number? Because if it's a very low Reynolds number, say 0.06 or 0.1, what would be the effect of those particle migration at that Reynolds number?
So the model is for a small Reynolds number. I said the particle Reynolds number had to be much less than 1.
Okay.
Yes, that's really important. It's a good question. So just coming here, you notice I've got that the flow Reynolds number can be between 1 and 100. Okay. That's typical what we see in experimental work. That seems to be a typical range.
Okay.
The particle Reynolds number is about 2 orders of magnitude smaller. But if you think about a flow Reynolds number of 100 and a particle Reynolds number of 10 to the minus 2 times 100, we've got an order 1 particle Reynolds number.
Okay.
So then my assumption here that the particle Reynolds number is much less than 1 is not true.
Okay.
So that can affect the outcome. So this model is for small particle Reynolds number, and to crank up the Reynolds number of the flow and of the particle, we'll have to do some more work. Okay. You can sort of get away with it to some extent. I mean, that's even true in normal fluid mechanics. You can have use a Stokes flow for a Reynolds number of about 100. Seems wrong, but you can still get good information out of it. But nevertheless, it's not quite right. So.
Okay. Yeah. Thank you.
Do we have any other questions for Yvonne there? Okay. Well, thank you very much once again for your talk, Professor Stokes. That was really enjoyable. That was a great talk. So thank you very much. And thank you to everyone for attending. And we hope to see you all next week.
Thank you.
Thanks, everyone. Bye.